All right, we're going to be talking about two other properties that are quite important to Markov chains. The first one has to do with periodicity. All right, there are going to be some states that we're going to see that get revisited in a periodic fashion. The other property that we're going to look at is something called positive recurrent Markov, or positive recurrent property. Basically, it says the time it takes to return to a state is finite. Okay. So what we're going to do is we'll go through the two of these. And when we put them together with a third property, which is we have a finite Markov chain, then it's going to be something called an ergodic Markov chain. And this property is going to be really important because it's going to allow us to use our P matrix in order to find some limiting probabilities. And we'll sort of get into this a little bit later. But for now, let's sort of think about periodicity when it comes to a Markov chain. So let me start by giving a very simple example that will get you thinking about periodicity. So let's say we had these two states, state 1 and state 2. And with probability 1, you go from state 1 to state 2. And with probability 1, you return from state 2 to state 1. And so if we were to look at a trajectory, let's say you started in state 1, then you would go from 1 to 2, back to 1, back to 2, back to 1. And this would keep repeating. And so in this way, we can see that the state 1 is periodic, right? It shows up every second time. Likewise, the state 2 is periodic. It shows up every second time. So in fact, this Markov chain is going to be, well, not just the chain, but the states. So state 1 is periodic. With period 2. Now, it ends up that periodicity is a class property. Okay? So if you remember from the last videos, we talked about different types of classes. There were recurrent classes, transient classes, and then we'd have sort of these absorbing states, right? So each one of those classes all the states inside of a class all have the same property. Now, in this case, 1 communicates with 2, right? Back and forth. So from 1 I can go to 2, so 2 is accessible from 1, and 1 is accessible from 2, and therefore they communicate. And in fact, there is a class with the states 1 and 2, okay? And so when I say that periodicity is a class property, what I mean is if 1 is periodic, any other state that is in the same class as 1 is also periodic. Okay, so this was a pretty simple example. Let's do something maybe a little bit more complicated that gets us looking at these different ideas of classes. So we'll do this. So 1. All right. So here we have 3 nodes, 1, 2, and 3. 2 is going to be an absorbing node. All right. So we can actually pull out what the different classes are pretty quickly. So in terms of the classes, we can see that 2, because it's an absorbing node, it communicates only with itself. Okay. we see that 1 communicates with 3 and 3 communicates with 1, so we have another class, 1 and 3. All right. So if we want to sort of draw this, this is one class, and then we have the second class. All right. The other thing that's worth noting is that if we look at this second class right here, we should see that this is transitive class. Pretty much any time you have a class that's connected to an absorbing state, right, or you have probability going out of that class, right, then it's almost always going to be transitive. Okay, so just something to think about. Okay, so let's sort of look at what's going on here. Because in many ways, this has the same structure as the previous problem, okay? So if we just look at this one class, let's say we pulled out this class right here. Where we have state 1 and 3. What we see is they bounce around to each other, right? So with 0.6 probability, you go to 1, and with 0.4 probability, you go back to 3. Now, the problem is the remaining 0.4 goes to node 2, and the remaining 0.6 from state 1 goes to the absorbing node as well. Okay, so what's going to end up happening, what we're going to see, is that not only are the classes 1 and 3 going to be transitive, but what we'll see is that they're also going to be periodic. Okay. And so what I want to do is give you the quick test to actually show you how you can check for periodicity. Okay. So the way that we're going to go about doing that is we're going to start by defining our transition probability matrix. Okay. And it's going to be 0, 0.6, and 0.4. Then we'll have 0, 1, 0. And finally 0.6, 0.4, and 0. All right. The way that we're going to check periodicity is by taking this P matrix and raising it to the n power. And we're going to take it to the n power when n is equal to 1, 2, 3, 4, 5, and 6, and so on. All right, so let's sort of do that. So we already have P to the first, but I'll go ahead and write it down again. 0.6, 0.4, 0, 1, 0, and 0.6, 0.4, 0. Right. So this is going to be our P matrix. So what we're going to do is we'll take P squared. Right. And so what this is going to do is it's going to tell us, well, what's the probability of getting from any one node to another, taking 2 steps. All right, so if we do that, we get 2, 4, 7, 6, 0, 0, 1, 0, and 0, 0.76, 0.24. Now I'm going to do P to the third power. And finally, I'll end with P to the fourth power. And what you'll see is we're going to sort of generate this pattern that you can sort of figure out after a little bit. So this P to the third is given by the following. So we have our p to the some power, and what we're going to pay attention to is what's happening along the diagonal. So again, we should think about what's going on. So a state is periodic if we can only come back to that same state on fixed intervals. Okay, so again, for state 1, we could only return to state 1 after we had gone to state 2, right? So we had 1, then we had to visit another state, then we could return to 1. Okay. With state, in this problem, with states 1 and 3, we're going to have the same problem, right? In order to return back to 1, we have to visit 3, and then we can go to 1. Right? And so this defines sort of this period of 2 as well. And in fact, we can see it in the Markov chain, right? So we can say, well, when do we see that the probability of returning to the state is non-zero? Right? So what you can see here is we have 0 to go from 1 to 1, from state 1 to state 1 in 1 time steps, that's 0. Then, in 2 time steps, we revisit with 0.024 probability. In 3 time steps, we can't visit state 1 from state 1. And then in 4 steps, we could visit it again, right? So again, from 1, we can't get to 1 just on its own, right? But in 2 steps, we can go 1, 3, 1, okay? Now, 1, 3, 1, 3, we can't get back, right? But if we take 4 steps, we can get back, right? And we see that pattern emerging here, okay? So the way that we're typically going to check for periodicity is you're going to find p squared, p3, p4, p5, p6, all right? And you're going to write down the diagonal values, okay? So what you're going to do after you multiply these out, so again, do these on your exam, it's always important. You're going to write out, well, let's see what p11 to the n power is, and let's write down this sequence. Okay, so we started off with 0, right? Then we had 0.24, then we had 0, and then 0.567, and then we have 0. You know, and this keeps repeating between 0 and a number, 0 and a number, 0 and a number. And what that tells us is that state 1 has a period of 2. All right. Now let's check out what happens for p to the n for the second state. Well, here we just see 1, 1, 1, 1. And that kind of makes sense because it's an absorbing state. All right. Now, in this case, state 2 is aperiodic. Okay? Because it doesn't have a period, right? We never see zeros in that diagram. Okay, so now let's look at the third state. And again, we're going to pull out how long it takes to go from state 3 back to state 3. Or what's the probability of going from state 3 to state 3 in n steps. Okay, so this was 1 step, 2 steps, 3 steps, 4 steps. We're going to pull out this diagonal element right there. All right. And so what we end up with something like 0, 0.24, 0. Ooh, something's not right there. I think I wrote something wrong. Ooh, that's wrong. Sorry, that's wrong. Yeah. 0.0576, 0, ... And again, what we're going to see is that state 3 is periodic. And it's going to also have a period of 2. All right. And again, we should kind of expect this because state 1 and state 3 are part of the same class. And so, in fact, they're going to end up having the same period. All right. Now, we could certainly have more complicated Markov chains. There's no reason why we need a period of 2. Right? So let's draw one. Let's draw a Markov chain that's a little bit more complicated. Actually, we'll keep a simple one. There we go. So here's just sort of a cycle where with probability 1, they're always making a jump. Okay. And so it should be kind of apparent that all these nodes form a class. So the class contains 1, 2, 3, 4, and 5. All right. And so it should sort of make sense that the time it takes to return back to 1 will always take 1, 2, 3, 4, 5 steps. Okay? And so what's going to happen is state 1 is going to have a period of 5. Okay? Not only that, because 2, 3, 4, and 5 are all part of the same class, they're also going to have a period of 5. And again, you can check this. You can make the matrix up, the P matrix, and then raise it to the first, second, third, fourth, fifth power. Right? At the fifth power, you'll see that you get diagonals full of 1s, or a 1 for the 1, 1. And then you go 5, 6, 7, 8, 9, 10, and you'll see a value pop up again. All right. So in fact, if you look at state 1, so actually let's do this real quick. All right. So this matrix looks something, I think, like this. 1, 2, 3, 4, 5. Okay. So this is the corresponding transition matrix. And if you pull out, you take p to the, well, we already have p to the 1. You get p squared, p cubed, p to the 4th, p to the 5th, p to the 6th. All right. What you're going to end up with, and you pull out, let's say the first value, this 1, 1. I'm not sure exactly what it is, but you should see something like 0, 0, 0. Actually, I'm going to check this. I'll do this real fast. So I went ahead and did it on Octave. So I'll just sort of show you what ends up happening. You get all these, the matrix kind of just shifts in a weird way. So you get something like that. I'll do p to the third. Okay, so you get something like that. And what ends up happening on p to the fifth, you finally get a 1 in this 1, 1 row column. And in fact, you get the identity matrix. Now, so if we look at, well, what's P11 as we raise it to the n, and what's that sequence? It's going to go 0, 0, 0, 0, 1. All right. And if we get P to the 6th, 7th, 8th, 9th, and 10th, we're going to see 0, 0, 0, 0, 1. This is P to the 10th. All right. And again, if we keep doing that, we'll get 0, 0, 0, 0, 1. Okay? And so what this tells us is that we have a period of 5, right? Because we see this non-zero value every fifth. Okay. Let me see if I can think of another weird one. Sometimes it's not always as apparent as we might think. All right, so I'm going to think up one real fast. Oops. Okay, so here goes a much more complicated Markov chain. And here you can see I have the states 1, 2, 3, 4, 5, and 6. So we got 6 different states. And they're sort of bouncing around all over the place. So it doesn't look like there's some clear structure, right, where, you know, we see them going back and forth necessarily, right, because we got these loops in weird places. And so it's not readily apparent whether or not this is a periodic Markov chain, or all the states are periodic or not, okay? And so what I want you to do is to give this problem a shot, all right? So go ahead and type in this P matrix, all right, into Octave or do it in your calculator. And again, figure out, well, let's look at P11 as we raise it to the nth power, okay? Look at P22 as we raise it to the nth power. And look how these numbers change, okay? So go ahead and do that. What you should see is there is a periodic structure. All right, so I'm going to stop talking for a second or two. Why don't you go ahead and pause and actually work this out in MATLAB. Calculate p squared, p to the third, p to the fourth, p to the fifth, p to the sixth, and look at what's happening to the very first element in the matrix. Okay. All right, so I'll stop talking. All right, so hopefully you've got that done by now. And what I did is I went ahead and did it in Octave. And I ended up, when I pulled out this first value, I got 0 here. Then I got 0.45, 0, 0.664. All right, so that was to the 4th power. Let's see if we can... I got 0, and then I think 0.58, something like that. All right, so what this is telling us is that P1, or this first state, state 1, has a period of 1, or 2, sorry. It's got a period of 2, right? And we see that because the only time that we can leave state 1 and return is even numbers. So we get 2, 4, 6, 8, and so forth. Okay. All right. Now, there is one little trick that I want you to be careful of because it'll probably pop up on a problem. So let's say And I'm not gonna give you the exact matrix, but you just need to be careful of it. So let's say we did this procedure, right? So I gave you a Markov diagram. You took P to the sum matrix, and you noticed the following pattern. So let's say we looked at some PII to the n, and you got 0, 0, 0, 0, 0.5, 0, 0.3, 0, 0.1, 0, 0.05, 0. All right. So you start getting this pattern here. All right. Now the thing is, it's not, it's not so clear what the period is immediately, at least in these first few steps. But what you do see is that at some point, you can only get non-zero values at, what is it, 1, 2, 3, at the 5th, 7th, 9th, 11th, and let's just assume that pattern continues, okay? So if you ever see something like this, don't be thrown off by these first few zeros, all right? Look for the pattern that emerges, okay? And so in this case, whatever the state I is, it's going to have a period. Well, this particular one has a period of 2, okay? We see that right there. Okay, so at this stage, you might think everything is periodic. Well, that's absolutely not the case. Most of the problems that we deal with are not periodic. All right, so let's sort of pull out a quick example of a non-periodic matrix. Okay, so, or Markov chain, sorry. All right. So here goes an example where we don't have a periodic Markov chain. And in fact, one of the biggest dead giveaways of not having a periodic Markov chain is if you ever see a self loop, then you know your Markov, or you know at least this state, 1, the state with the self loop is not periodic, right? It's going to be aperiodic, okay? Now the question is, does 1 communicate with all these other guys? Oh, in fact, it doesn't. So let's fix this. I'm going to make this 0.75. Okay. So the question is, how many different classes do we have here? Well, 1 can access 3, which can access 2. 2 can access 3, which can access 1. And so it ends up, what we see, if you look at this, is that we have a single class with 1, 2, and 3 in it. All right? And because 1 is aperiodic, we know that 2 and 3 are also aperiodic. And that's because periodicity is a class property. All states that are aperiodic, okay, or all states in the same class share the same period or periodicity, whether they're periodic or aperiodic. Okay, so what I'm going to do is let's actually write up what this transition matrix is. All right, so we're going to get something like 0.25, 0.5, 0.25, 0, 0, 1, and then 0.25, 0.75, 0. Okay, so what I want you to do is take this P matrix to the 1 power, 2 power, 3 power, 4 power, and so forth, and pull out those diagonal terms to figure out whether or not this Markov chain is periodic. Okay, so hopefully you were able to enter in this matrix into Octave or into your calculator and take it to the 2, 3, 4, 5, 6, and so forth power. So what you see here is I've written down the transition matrix to these different powers up to 4. And what I've done is I've gone ahead and pulled out the values in this upper right-hand corner for the state 1. And so I've written them here. And what you'll see is a 0 never pops up, okay? And right here, this is a clear indication that state 1 is aperiodic. Okay, so it doesn't have a period. All right, so the big question might be, well, how many times do I have to take p to the n power to figure out whether or not there's a period? Well, a good rule of, well, usually you'll see it within, let's say, the number of states that you have, right? So here I have 3 states, and so oftentimes what you'll see is you can't have a period longer than the number of states that you have. Okay, so in fact, this is a property of Markov chains, which is that the periodicity is limited by the number of states you have, but not only that, by the number of states that are in the class. Okay, so in this case, 1, 2, and 3 are in the same class. So the size of that class is 3, and the largest period that we could have is 3. And so when you go through this procedure, all you'd have to do, well, typically you do it up to the 3rd power, and you'd see, does a 0 show up, right? And then a non-zero value, right? And so normally you'll see it within the first 3. Now that rule of thumb doesn't always work, because if you remember, I said, well, sometimes you might get something like 0, 0, 0, 0.5, 0, 0, 0.3, 0, 0, 0.25, okay? So if you're to see something like that, right, you kind of just ignore these first few values and you say, well, I see here that I have a number, then 0, 0, a number, 0, 0, a number, okay? And so what that tells us is that, in fact, we have a period of 3. Okay. Okay. But it might have taken some time for that pattern to be established, right? We had a bunch of zeros beforehand. Heck, you could have like 20 zeros beforehand, right? It just depends on how many states you have, okay? So typically, the amount of time you have to wait before you see a pattern emerge is you could see it as quickly as the number of states you have, 3, but you should definitely see it within twice that number, okay? So if I don't see a pattern here, by the 6, p to the 6th power, then I know I'm probably not, or I know I'm not periodic, okay? Because I only have 3 states. And so the period will emerge within the first 6 steps. If it doesn't show up in 6 steps, then we're not periodic. All right. So I'm sure you guys have plenty of questions. Usually I get, well, what about this? What about that? What I suggest you do is make up your own Markov chain and test it out. I think that's the best way for you guys to sort of play around with it and see how we might generate these patterns. You know, a good way for maybe something like that to happen. I don't know. I'll think about it. Maybe I'll give a problem. I know there was one on the exam or practice exam at one point, so it should pop up. So this is an aperiodic state. In fact, most of the problems we've seen so far were in fact aperiodic. So this is going to be more typical than not. All right, so that is the video on periodicity or aperiodic Markov chains, depending on how you show it. What we did here is we tried to figure out or determine what the period is. If you don't see a period where you just see numbers, non-zero values the whole time, then you're aperiodic. All right. So in the next video, we're going to talk about positive recurrence.